We're very happy that our colleague Yi-Zhi is giving today's talk. Yi-Zhi needs no introduction. Yi-Zhi's title is Representation Theory of Vertex Operator Algebras in Conformal Field Theory.
Okay, thank you. So see this talk, in this talk I want to actually summarize the progress in a program to construct conformal field theory in the sense of Kontsevich and Segal, using the approach of representation theory of vertex operator algebras. So this program started more than 30 years ago. It's a long-term project, so it is still not actually it is still far from finished. But for rational conformal field theory, the most of the major problem has been solved, but there are still some analysis. See, there are a lot of algebra, but also a lot of analysis. There are still analysis problems need to be solved, but see, I expect that these are not major problems. So rational conformal field theory probably we can actually solve, actually finish the construction in a few years. But for non-rational ones, okay, there are a lot of open problems. So I want to actually summarize, give a survey on these progresses. Okay, so this is the plan. First of all, I want to discuss the definition of conformal field theory. This is the definition in the sense of Segal. Kontsevich Segal, and also Segal, he gave much more detailed definitions, including chiral ones. And then I certainly want to discuss the representation theory of vertex operator algebra and this program to construct conformal field theory in this sense. And then see there are these major progress actually during the study of this construction. So including these modular functors, the Berliner formula, and the modular tensor categories. And then see basically the modular functor, Berliner formula, and the modular tensor categories, they can actually, especially the modular functors, and this can be actually immediately includes the high genus. Okay, but see, even if you have a high genus modular functor, you still do not have a high genus conformal field theory. So we still so this part, the part 3 is still about genus 0 and genus 1. And then see the important thing is to actually give a construction of a high genus theory. So for high genus theory, it's this is the actually inspired by the work of the construction by the proof of the factorization theorem by two people who are presented here. So I will mention this. The NC Bingui, he actually solved a major conjecture. Then you see I will talk about the current status. Okay, so this is the plan. Okay, let me first discuss the definition. Okay, so yeah, I just want to say that this is a survey, so I cannot get into any technical details because there are a lot of papers have been devoted to this. So I would see the technical thing. You can always find them or just email me to ask for more details. So just before the definition of conformal field theory are given, there are a lot of work already done. So first of all, just to mention that in this talk, I'm only talking about two-dimensional conformal field theory. For high-dimensional conformal field theory, for example, one of the most important one is the four-dimensional supersymmetric Yang-Mills. There's no precise mathematical definition even. Okay. So the first formulation is actually given by Belevin, Polyakov, and Zamolodchikov in 1984. They used the operator expansion. Okay. And then see the actually there was a former student of Jim, Tsukada, who actually who's the mathematical advisor is actually Igor Franco, but see he was at the Rutgers under also supervised by Jim. So he constructed the lattice vertex operator using the path integral approach. Okay, so in this case, the path integral approach works because there's no interaction term. You do not need to do the normalization and so on. So from this construction, Igor Franco actually obtained the geometrical interpretation of these classical vertex operators. They must correspond to some geometry objects. So actually, they correspond to these surface like a pair of pens. Okay, so then see the Franco gave the geometrical interpretation of the associativity property. So these are all before the formulation of conformal field theory. And then in physics, okay, we have the work of Frieda and Schenker. They give a formulation of rational conformal field on hygenous Riemann surfaces. They actually emphasized the importance of modular space. Okay, so this is the first emphasis by physicists. And then see the around the same time, basically probably a little later, Verlinde actually formulated the Verlinde conjecture and derived the Verlinde formula. So this is a major progress. And then certainly one of the most important progress in rational conformal field is the work of Moore and Seiberg. So this is really a landmark important work. They actually proved the following. So they first assume operator pro expansion and modular invariance for chiral vertex operators. And then using these, so these are clearly conjectures if you look at their papers, because they stated these, but certainly there's no proof. So these are conjectures, and then they derived the Verlinde formula. Okay, so this is a really nice conceptual understanding because it reduces some mysterious formula like a Verlinde formula to conceptual conjectures. But these conceptual conjectures are actually the harder to prove. Okay, and then see the Moore-Seiberg also derived their proof is that they derived a set of polynomial equations from these conjectures, and then Verlinde formula is just a property of these solutions. So this is how they obtain the Verlinde formula. And now see the essentially, I think probably around the same time when Moore-Seiberg, see, actually Moore-Seiberg, if you look at Moore-Seiberg's paper, they actually refer to Segal's definition. So, but see in their long paper, in the 1988 paper, they refer to Graham Segal's definition, but in their 87 paper, they actually did not. Okay, so probably around the same time. So the definition of conformal field theory are given by both Kontsevich and Graham Segal. So Kontsevich never published a paper giving this definition, but see, he gave a talk about the definition. Actually, you can find the evidence in a massive review of one of Graham Segal's announcement that Kontsevich gave such a talk. And Kontsevich actually himself told me when he was at the Rutgers a long time ago, he told me that he also gave the definition. And Segal actually gave a number of talks. I actually was at Segal's talk in 1987 at IAS. Then he has this manuscript, okay, which is famous and later was published in 2004. So the definition is, roughly speaking, is this. It's that Segal introduced the category formed by Riemann surfaces with parametrized, oriented, and ordered boundary components Then he defined the conformal field theory to be just a projective functor. So because you have a category, then you can talk about a functor from this geometry category to the category formed by tensor powers of, in general, it should be complete locally convex topological space. Usually it's a Hilbert space, but in general, it might not be Hilbert space. You certainly have to have a non-degenerate Hermitian form, satisfy suitable natural condition. It's a functor satisfy natural conditions. So let me give you a picture here. Okay, so here is a picture of description of Segal's category. That is, the objects are circles. Okay, copies of a number of copies of circles. So there are two objects, and what is the morphism? It's just the Riemann surfaces with the corresponding boundary to be parametrized by these circles. Okay, so these Riemann surfaces can be composed. Okay, so you can compose two morphisms. So that's why it forms a category. But see, the one thing is that category is a very bad thing. See, the category, if you use a category, you cannot talk about things that are equal. Usually you have to talk about things that are equivalent, which is up to some kind of isomorphism and so on. So if you use the category language, there are a lot of complications. So this is Igor Chris, he actually observed that if you use category theory, you have a lot of complications. But actually, conformal field theory, we do not need a category. We only need some property of these modular space of Riemann surface, and they actually form what people call the props. This is some kind of objects actually giving some kind of multi operations, which is actually before the language of operands. So it is better to use this. Then you see what is a prop? It's just a sequence of sets of elements with m inputs and n outputs. Okay, so this is exactly the kind of Riemann surface I draw. You have three inputs and two outputs, right? And then you can do some composition. So then we can talk about an algebra over a prop. It's just we have if you are given a prop of Riemann surface, say, and then see the tensor power of vector space or Hilbert space will also form a prop. All the tensor powers. So an algebra is just a homomorphism of prop from some prop to this particular prop. And then see there is the complication of a conformal anomaly. Okay, so the conformal anomaly is given by the determinant line bundle over the modular spaces of Riemann surfaces with parametrized boundaries. And so on. Okay, so the main thing that you take the tensor product of a power of determinant line bundle with a suitable power of its complex conjugation, and then these also form a prop. Okay, so it's not just a modular space. You have to consider determinant lines and its complex conjugation, and then this will give us the conformal anomaly. So now, what is the conformal field theory? In the sense of Segal, it's just an algebra over such a prop, the prop of the tensor product of a power of determinant line bundle with a suitable power of its complex conjugation. So, and then it should satisfy some natural conditions. So see, I would later I will mention this high genus solving type of things, but I will omit the details. So roughly speaking, this is a definition of conformal field theory. Okay, now actually, if anyone who try, okay, you can just try, because this definition is quite simple. It's not difficult. It's very natural. You can try to construct. then you will find that it is extremely difficult. It's almost impossible if you just want to start with the definition to construct. So what happened in physics is that physicists, they always assume things to be analytic. So actually they find that the conformal field theory can be decomposed into the chiral part and anti-chiral part. That's the analytic and anti-analytic parts. So then they only study the analytical parts. So, but see, when you study only the analytical parts, you will have multi-valued functions. So that is the major complication. But it is because of this major complication that you will get all these wonderful structure, like the Bray group representations, three manifold invariants. They all coming from this decomposition. Okay, so because of this, Segal actually introduced a notion called the modular functors. So yeah, so the conformal field theory study using their chiral and anti-chiral parts. So in order to describe these parts, Segal introduced the notion of modular functor and a weakly conformal field theory. So I just want to emphasize that modular functor is a part of conformal field theory, but it is far from conformal field theory. So modular functor is that you still need Riemann surfaces with parameterized boundaries, but we also need them to be colored, labeled, and ordered. Here the label is mainly see the in vertex operator theory. These are labeled by irreducible modules for the for a vertex operator. And what is a modular functor? It's a functor from the category Riemann surfaces with these boundary components to the category of finite dimensional vector space. And then they certainly should satisfy some properties that, again, I omit these details of the properties. The Segal used the functorial language, but see actually you can formulate them just using modular space. So the modular functor is a finite rank holomorphic bounded over the modular space of such Riemann surface and satisfying natural properties. So this is a modular functor. Okay, now see the main thing that even if you can construct the modular functors, it's not enough. You still need to construct the so-called weakly conformal field theory, which are exactly corresponds to so-called chiral conformal field theories. So given a modular functor, we can actually construct a prop. So it's a vector bounded over the modular space of Riemann surfaces. And these also have these like the sewing operations, so they also form a prop. And then the a weakly conformal field theory is nothing but an algebra over such a prop. Okay, and it certainly satisfies some additional axioms. And then see the main thing that Segal also discussed that if you have two weakly conformal field theories with non-degenerate bilinear forms on the fibers of the modular functors and satisfy some condition, we can put these two weakly conformal field theories together to give a full conformal field theory. So if you have a weakly conformal field theory satisfy all nice properties, then you can put them together to form a full conformal field theory which satisfy the original definition of Segal and Kontsevich. Okay, so this reduced the construction of full conformal field theories to the construction of modular functors and weakly conformal field theories. Okay, so now see this is about definition. So now we have to discuss the representation of vertex operator, right? Because our program is to use the representation theory of vertex operator to construct these conformal field theory. Actually, yeah. So we this is the program I want to discuss. Okay, so I would not, because again this is service, I would not give any technical definition of vertex operator, but just to discuss some briefly some things related to conformal field theory. So first of all, you see, in the original formulation of Belivan, Polyakov, and Zamolodchikov of conformal field theory, they actually formulated the operator expansion for general chiral conformal fields. Okay, so certainly these are in general multi-valued, but we can consider only meromorphic fields. Then see, if you only consider meromorphic fields, you have the operator product expansion of a meromorphic fields, then actually you will get vertex operators. So certainly these are not formulated precisely. The precise definition of vertex operator was given by Borcherds and also by Frank Lepoussin-Merman in a modified form. So then see the I think that see this is actually my work. I was done at Rutgers under the direction of Jim. That I actually gave a geometric definition of vertex operator. Okay, so basically it just define vertex operator as some kind of algebra over some operator. So operator is for proper. I said that you have m inputs and n outputs. Operator is similar to proper, but has only you have m inputs, but has only one output. Okay, this is more like an operation, because operation is always you have n elements multiplied together to give you one element. So vertex operator is in this definition is some kind of an algebra over the operator given by Riemann sphere, okay, with m incoming like the boundary components or punctures and local coordinates, and one outgoing ones. So roughly speaking, it's just this, okay, but there are some kind of a condition like a meromorphicity and so on. So this is the you also have to take care of the determinant line bundle. So there's a complex power of determinant line bundle. In the Riemann sphere case, everything is well defined. So this is the geometric definition of vertex operator. Okay, this is a very nice. Then you see the when you have vertex operator but looks completely geometric, then certainly you wanted to see whether you can use the vertex operator to construct a conformal field theory. Okay, so yeah, so this is the certainly the in the beginning I myself also just to try to construct conformal field using vertex operator. So the first step is actually see that here I just want to mention that actually if you just want to use vertex operator, you will find that it's impossible. But in one particular case, it is possible. Certainly, this is still not completely worked out yet, okay, because as I said, we still have this analysis problem. But it is possible is because if there is only one irreducible module, that is the vertex operator itself, then it is possible to construct conformal field theory using only the vertex operator. So for moonshine module, for example, you do not need anything else. But it is in general impossible to use only vertex operator. You must use modules and intertwining operators. So this is something that I will actually discuss more because this is crucial. So because of this, the program to construct conformal field theory, you have to start with modules and intertwining operators. You cannot just use vertex operator, okay? So because of this, it's not just about the vertex operator, but it is indeed about the representation theory of vertex operator. So that's why in the title, it is called a representation theory, not vertex operator. Without modules and intertwining operators, these representation theoretic objects, we will not be able to construct conformal field theory. Okay, so now let me discuss module, why we need modules. So here, the main thing is this. we actually, I already show that the vertex operator algebra is genus 0 objects. So the first step is try to construct these genus 1 thing. So then you see the main thing that the simplest genus 1 objects are characters of these modules for vertex operator algebra. And one particular class of vertex operator algebra are from alpha and Lie algebra. We have these integral highest weight irreducible modules, and the character for an alpha and Lie algebra of these things is not invariant under the modular transformation. Okay, so the character of 1. Okay. Instead, if you take the characters of all such modules and then put them together, you span a vector space. That vector space is invariant. Okay, so if you take for example alpha and Lie algebra vertex algebra, you will not be able to get a modular invariance. But you have, if you take all the irreducible modules, you put them together, you do get modular invariance. It's a space which is modular invariant. Okay, so this is earlier in the study of alpha and Lie algebras. And then you see the in 1990, Zhu actually proved that given a suitable vertex of satisfy some condition like a C2 cofinite and a complete reducibility, he proved the modular invariance of a space of such characters of irreducible modules for a general vertex operator algebra satisfy some condition. Okay, and then see this is Zhu actually, what Zhu proved is a special case of the Moisseiberg conjecture on the modular invariance of chiral vertex operators. Okay, because of this, okay, the character of a vertex, if you just take a vertex operator algebra, it is not invariant under the modular transformation. Therefore, okay, you cannot formulate something on the genus 1 using only vertex operator algebra. So this is the reason why we have to introduce module. So it is impossible to construct genus 1 conformal using vertex operator algebras only. We have to consider modules. Okay, so if we consider modules, okay, then we have to consider conformal fields between modules, right? So if you only have a vertex operator algebra, then you see these vertex operator acting on vertex operator algebra is enough. But see, if you have different modules, you have to consider conformal fields between these modules. So these are just the intertwining operators. So the intertwining operator without logarithm, actually, it's already studied in the work of Belyov, Polyakov, and Zamolodchikov. Certainly, they assume everything has have the operator product expansion. So operator product expansion is a major conjecture. So these intertwining operators are called chiral vertex operator by Moisseiberg. In mathematics, we call this intertwining operator, and this was first introduced in mathematics by Franco, Jim, and myself. And then you see the later actually physicists actually they find that a logarithm intertwining operators with logarithm actually is needed. You cannot for some theory you cannot avoid putting the logarithm in. Okay, so these are logarithm intertwining operators, and in mathematics they were first studied by Miles. So mathematically, you see if we want to construct a conformal field theory, we actually now have to study the genus 0 theory for intertwining operator. So we have to prove the operator product expansion or associativity, which are equivalent to operator product expansion. And also we have to study the genus 1 theory, that is the modular invariance for intertwining operators. So these are two major conjectures formulated by Moore and Seiberg. Okay, so here let me first discuss the operator product expansion or associativity for intertwining operator. So yeah, again, see I said that I would not give technical details, so I do not really write down formulas. You can find them in all different papers. Here I just wanted to discuss what kind of results we get. So yeah, so as I said, this is one of the most fundamental conjectures in the work of Moy-Seiberg. So here I just give the most general results. Okay, so the most general results in this case is that if we assume so-called every grading restricted generalized margin. So because I didn't give technical details, so I do not give the definition, but you just think that there is a kind of a module for the vertex operator algebra. They should be satisfy some finiteness condition. We call this C1 cofinite. Okay, this is weaker than C2 cofinite is introduced by Zhu. And then see every low bounded generalized V module generated by generalized eigenvector for L0 in the dual space of the tensor product of two such modules is again grading restricted. Grading restricted means that the homogeneous subspace are finite dimensional and it is also lower bounded. Then we have the associativity or the operator product expansion. Okay. These are proved. See the in various different under various different assumptions. So the first the assumption is stronger, and then we actually have the weaker assumptions. Okay, so this is the operator approximation results. So this is solved one of the Moy-Seiberg's conjecture in the rational conformal field theory case. It also proved the operator product expansion in the logarithmic case under these conditions. So the second main conjecture of Moy-Seiberg is the modular invariance. Okay, so yeah, this is the second one. So here again, so I just want to say that this is mainly it is okay. It has been published that the modular invariance for rational conformal field theory. It's already published. So here's the statement. So first of all, the vertex operator algebra has only has only non-negative weights element, and the space of weight 0 is one-dimensional. I think that probably the space of weight 0 is one-dimensional is not needed. I think that in my proof of linear formula this is needed, but see this here probably this is not needed. I need to check because I do not think that I need that. And then the second condition that the vertex operator is C2 cofinite. This is the condition introduced by Zhu. And then the third condition is complete reducibility. Okay, you can always write every reasonable module as a direct sum of irreducible modules. Then when you take the products of intertwining operators and then take some kind of a Q trace, and then the space of Q trace are invariant under modular transformation. So this actually gives us a vector bundle over the modular space of genus 1 surface, Riemann surfaces. Okay, so that's give genus 1 conformal field theory. Now, in the case that the vertex operator algebra is not completely reducible, the modules are not completely reducible, means that only 1 and 2 are satisfied. Okay, very recently, I think that I worked out a proof based on the work of a former student of Jim and I, the Francesco Fiordalisi. The recently I actually proved that we can obtain some intertwining operator from some kind of a symmetrical linear functional. So this is the last step. Actually, we haven't worked out. So I think I can do this. So this modular invariance now should be fine. Okay, but the paper is still in preparation. So I do not have any papers to talk about yet. Okay, but CD, I believe that this is that. Okay, I will talk about this later more. So now let's look at, okay, so I discussed some results in the representation theory of vertex algebras, okay, which are needed for the program to construct conformal field theory. So now I want to discuss some major results, okay. So first of all, using the associativity for intertwining operators, we can construct these multi-correlation functions using the analytic extensions. And then modular invariance of intertwining operators allows to construct the genus 1 correlation functions. So here, the associativity gave us actually the genus 0. I should write genus 0 correlation functions. The modular invariance gave us genus 1 correlation functions. So these give holomorphic bundles, holomorphic vector bundles over these modular spaces. And these vector bundles actually give us a modular functors. It's not just genus 0 and genus 1. It's a high genus. So this, you can find this in Trave's book. He actually, if you want to construct high genus modular functor, you can just put the lower genus 1, genus 0 and genus 1, put them together. You will get a high genus modular functor. But the main problem is that we need to construct conformal field theory, not just the modular functor. Okay, so first step is certainly genus 0 and genus 1. Okay, so the interesting thing is this. See, in physics, because Moyes-Seiberg assumed these wonderful properties of conformal field theory. So the linear formula is actually derived from properties of conformal field theory. But actually, it's the opposite. Mathematically, if we want to construct conformal field theory, we actually have to first prove the linear formula. So that's the amazing thing. Okay. So we see if we want to construct conformal field theory, especially the full conformal field theory, we actually need to construct a non-degenerate bilinear or Hermitian form on genus 0 modular functors first. See, if we want to construct the genus 0 full conformal field theory, we have to first construct this, so we can put chiral and anti-chiral part together. So the interesting thing is this: we actually only want to prove the non-degeneracy of these bilinear or Hermitian form on genus 0 modular functor, but the proof of this non-degeneracy actually needs the linear formula, or formulas used to prove the linear formula. So this is the amazing thing. So why it's amazing? It's because the linear formula says that the fusion rules can be expressed using the matrix of the transformation of the vacuum characters under this modular transformation. So the formula is actually a formula related to the modular invariance. Modular invariance is a genus 1 property. It's not genus 0 property. Okay, here we only want to prove the non-degeneracy in genus 0, but it turned out that we need a linear formula, which is genus 1 property. So it means that genus 0 property needs genus 1 property to prove. So this is something really amazing. So anyway, see, up to now, you can just find a different type of proof of our results. You always need things like Berliner formula or things equivalent to Berliner formula. So this is indeed what's going on. Okay, so the Mohr-Seiberg, they proved the Berliner formula under the assumption that the operator propagation and the modeling invariance are true. Okay, so because I proved these two conjectures, so indeed, okay, I also use these two properties to prove the Berliner formula. Okay, so the Berliner formula now is proved, and then see that we can actually construct the bilinear form and prove the non-degeneracy. So actually, the bilinear form is quite natural. You can construct a natural bilinear form. If we have a natural antilinear involution, then we have a Hermitian form. Okay. The main difficulty is actually the non-degeneracy. I already said that. Yeah. So here, this is something I already discussed. So the interesting thing that this is a genus 0 property, but surprisingly, we need the Berliner formula to prove this, which is a genus 1 property. So this was proved in a joint work with also a former Rutgers student, Liang Kong. He will give a talk on I think which day? So probably October 30th or something. Okay. So using this non-degeneracy, we can actually construct full conformal field theory. Certainly, these are called the diagonal ones. Okay, diagonal means that the chiral and anti-chiral are actually the same. So these are now genus 0, genus 1. Full conformal field theories are constructed. Okay, now another main results follow from these are the modular tensor categories. So the main thing that Mohr-Seiberg equation has all those properties similar to properties of tensor category. And then Trive actually, he formulated a precise notion of modular tensor category. The work of Mohr-Seiberg then can be reformulated as a conjecture that suitable modular categories for, say, for example, alpha Lie algebra, Virasoro algebra, and some real algebras, and so on, have natural structure of modular tensor category. So this is something that if you combine that, you get these precise conjecture. And using the results on the associativity of intertwining operators, then see basically Jim and I constructed the braided tensor category structure on suitable module category for suitable vertex operator algebras in the semi-simple case. And then in the non-semi-simple case, that's the logarithmic case. So this has been done by Jim, Lin Zhang, and myself. Okay. Then this is only about the braided tensor category. Then we have this modular tensor category. Then you see this is constructed by myself. Certainly the condition is stronger. And the interesting thing, which is related to the non-degeneracy of the bilinear form, is that the proof of the rigidity needs a formula used to prove the Berliner formula. So in some sense that the rigidity is equivalent to the non-degeneracy of the bilinear form. This is, I think this is true. Okay, so this is the results of modular tensor category. Okay, so now see these are actually only about genus 0 and genus 1 conformal field theory. Even though modular functor we have high genus 1, but conformal field theory, these are only genus 0 and genus 1. So now we wanted to discuss the high genus ones. So high genus ones, there are more complication because even like the parameterization of boundary components, you have to be more careful. So here the moduli space of Riemann surfaces, they are actually infinite dimensional because of the boundary parameterization. Okay, so for infinite dimensional objects, you want to give a manifold structure. So here I just want to say that for Riemann surfaces with parameterized boundary components, it's not like in algebraic geometry, you only consider Riemann surfaces with punctures. Then see the modular space is not a very nice space, but it's finite dimensional. The nice thing that's finite dimensional, but it's not a manifold and so on. But if you have parameterizations, it is a manifold, but it's an infinite dimensional manifold. And then the main thing that's what is the manifold structure? So it depends on how do you choose the boundary parameterization. So the simplest boundary parameterization is certainly analytical ones, but that's not good because when you take limits, it's not analytic anymore. So Segal in his manuscript, he considers smooth parameterization. So indeed, one can define smooth parameterization. You can also use the smooth parameterization to define sewing operations. So analytical one, for analytical parameterization, there's no problem to define sewing operation. But for smooth one, it's not obvious. But one can do that. But I should say that the manifold structure using smooth parameterization, it does not have nice property. Like it's not modeled on not modeled on Hilbert space and not even on Banach space. So it's bad. Okay, so this is the study of another former Rutgers student, Rennell, and his collaborator Schippers and Staubach. They for many years they studied these modular space. So they actually find that the so-called Riemann surface with WP class quasi-symmetrically parameterized boundary components are the most natural objects because the modular space of such Riemann surface is a complex Hilbert manifold. Okay, so it's really a nice structure. So they also proved that the sewing operation, it's not just only well-defined, but it's actually analytic. Okay, because the modular space has an analytic structure. So this is now become a really nice modular space. And to actually discuss these hygienist conformal field theory, we also need conformal anomalies. So here the determined line bundle is necessary. So they actually constructed this determined line bundle over this modular space because the boundary parameterization is different. If the boundary parameterization is not analytic, you have to be careful. So they find that determined line bundle is defined and is a holomorphic line bundle. Okay. So this is their modular space. Okay, now this is just a modular space, but we actually want to discuss conformal field theory. Okay. So the main thing that see the one difficult thing about conformal field theory is that it is non-topological, and therefore the Hilbert space, the state space, is always infinite dimensional, and therefore you always have to prove some convergence. So this is something that one cannot avoid. So here, in the genus 0 and the genus 1 case, okay, one of the main problems I solved are also the proof of this convergence. Okay, so without convergence, you just have some formal series. You cannot really talk about operator product expansion or modular events. So these are always the first problem one has to actually solve. So I do solved this problem. Okay, then if we want to construct a hygienist weakly conformal field theory, it is actually very easy to write down these formal series. That's no difficulty. Just like in the modular invariance case, genus 1 case, you just take the product of inter-20 operator, and then you take the Q trace, That's because you take trace on a infinite dimensional space, it must be a formal series. You have to prove its convergence. So here for high genus, you can still write down all these product of intertwining operators. But instead of taking one Q trace, you can take several Q trace. These are the candidates for the high genus correlation functions. So now, assuming that these are convergent, then it is very easy to show that the space of these correlation functions are invariant under the action of a mapping class group, because the mapping class group are actually given by so-called genus 0 move and a genus 1 move. So genus 0 move is the associativity, genus 1 move is exactly the modular invariance. These have been proved. So as long as you prove the convergence, the mapping class group acts on the space is automatic, almost automatic. Okay, so the main problem is the convergence. Okay, so this actually high genus convergence, I actually put this as a conjecture because I myself at that time still do not know how to do that. Okay, so now let me give you a picture because here I just without detail and then even do not give a picture, it's too difficult to imagine. So here the main thing is this: if we have such a Riemann surface, okay, and then you wanted to actually identify these two boundaries, this boundary and this boundary. After your identification, you get a Riemann surface of this form. So this is at the Riemann surface level. And we know that associated to each Riemann surface, there should be some correlation functions. Okay, so the main thing is that when you solve the surface to get this surface, it corresponds to for the correlation function, it corresponds to you take some kind of a Q trace of the correlation. So there is a correlation function on this space, on this the elements in the modular space. And after you solve these, you will get a correlation function on this surface by just taking some Q trace. Okay, so that is the Q trace. We have to prove that it is convergent. Okay, so that's the convergence problem. So actually, Bing Gui, he was at Rutgers last semester. He actually gave a proof of this convergence. So in the genus 0 and genus 1 case, the convergence is proved using some decomposition of meromorphic functions on genus 0 and genus 1 modular space. Okay, so this is how I prove these convergence. And for example, the Q expansion of a Weierstrass P function is actually a decomposition of genus 1 the meromorphic function into genus 0 meromorphic function. So no one really just stated the Q expansion in this way, but see, this is exactly how I use. So the main thing for me that I do not know how to prove the high genus convergence is that I do not know a decomposition of meromorphic functions on the modular space of high genus. Okay, so now here is the I want to mention that Damiolini, Gibney, and Tarasca, they actually proved the factorization conjecture for conformal blocks on high genus. So this is actually a very nice, important progress in the theory of conformal field theory, because the factorization property conjecture has been open for many years. And then see the inspired by their work. So basically, indeed, Bing Gui, he actually followed closely their work. And then he actually found that he can prove this high genus convergence. So what he used is an old decomposition theorem by Grout. So this is exactly the decomposition theorem I actually am not aware of. Okay, so he found that there is such a theorem, and he used this, he proved. So the convergence conjecture is now solved. So this is one of the main problem solved recently. Okay, now I wanted to finish this talk by just to give a quick discussion on the status of this program for the remaining things. So in the rational conformal field theory case, okay, so most of the problem has been solved. So Bing Gui, myself, and the Rennell, Shippers, and Starker, we are actually preparing a long paper to try to give this. Okay, there are still some relatively minor problems to be solved. The first is the sewing of the sewing isomorphism determine lines and also their analyticity. So we actually here have to main thing is to prove the analyticity of these sewing isomorphism of determined lines. So this is something that we are working on this. Okay. The second is the topological completions. So I just want to mention that in Segal's formulation, everything is like a Hilbert space or locally complete, locally convex topological space. Vertex of operator modules, they are just a graded space. So you have to give some topological completion, and topological completions are very, very crucial. Actually, because it contains all the hygienist information. So this is something that I expect that we can actually use all the results we have approved to construct such completion, but it still need to do some work, and we have to use this modular space of Rennell, Shippers, and Starbuck, because this is the modular space of the completion of the modular space with analytic parameterization. So it's a completion means that you have to take some kind of limits. So here we also need limits. Okay. So now finally, see the in the rational case, I also have a conjecture say that the topological completion construct using my method should be the same as the Hilbert space completion if the theory is unitary. Okay, so this is something at this moment I still do not know how to prove, but see, I hope that I will have some idea after I get to the completion. Okay, so this is the status about rational conformal field theory, and then non-rational ones. Okay, now rational ones, the operator product expansion has been proved using C1 confinedness and so on. Okay, so braided tensor category has been obtained. So this is the work by Jim, Lin Zhang, and myself. And then see the under the C2 confinedness condition, Fiordalisi, I already mentioned that he already proved a large part of the modular invariance. The main thing is that after his thesis, we still need a construction of intertwining operators from some symmetric linear functionals. So recently, I have given such a construction of intertwining operators. So I think that the modular invariance will follow from this. But these papers are in preparation. So I'm still writing the first paper. So it still takes a while. Okay, now in the non-semi-simple case, higher genus convergence is still not approved. Okay, so Bing Gui said that his proof need to use the complete reducibility. So high genus convergence is still a conjecture. Okay, it is even more difficult to actually even guess how do you put chiral and anti-chiral theory together. So this is something that I think that even in physics, people do not really know about how to put chiral and anti-chiral together. Some people have some example they can do that, but see, this is not some kind of a general principle. So this is a very sort of open problem. We do not really know. Okay, so this is about non-rational conformal field theory. So okay, so finally, yeah, just in this framework, I want to just mention some of the main problems, I myself found that it's extremely important. Okay. One important conformal field theory is so-called the Liouville theory. This theory now has a lot of activity. It's really a wonderful theory, but it's very difficult. But see, these people, they have constructed this theory using probability theory, okay? And they actually now have proved so-called conformal bootstrap hypothesis. Also use probability. So in this framework, we even do not know what is the correct vertex of algebra and what is the correct modules, because in this case, we have to consider continuous families of modules. So when you take a sums, if you want to take sum, it's not sum, you have to take integral. So this will be actually a very nice theory for actually generalize a lot of theory in the representation theory of vertex algebra. So the other important thing, I have just posed this open problem for many, many years, is that the conformal field theory, the associated to Calabi-Yau manifolds. We still do not know what is the correct vertex of algebra and the correct category of modules. Okay, so these needs to be addressed. Okay, so that's all my talk. I finished my talk here.
Well, thanks very much.
Okay, thank you.
Questions?
Yeah, hi. So Yi-Zhi, when you talk about the decomposition, I might not have been paying close enough attention. When you say that the Q expansion is a decomposition, what do you mean by that? Do you mean that the Q expansion factors in some way, or that you can, in other words, how do you see this decomposition? I mean, or maybe that's not easy to show.
Yeah.
Does it look like factors?
Okay, so, it's I do not see that. The main thing is this: it's that the Q expansion is the usually we would talk about the Q. You take the Q trace, okay, but certainly when you want to prove the modular invariance, you have the Q trace. After you take the modular invariance, after you apply the modular transformation, it's not a Q series anymore. It is just a function in terms in Q, and then you want to expand this into Q. That's the Q expansion. So that's the main difficulty one of the main difficulty when you want to prove the modular invariance. Okay, so like in the non-semi-simple case, in the logarithm case, the Francesco, he actually proved the Q trace is convergent, and you can and then extend it to some nice function on the modular space. Actually, not on the modular space, because modular space, the modular invariance has not been proved. So actually, he proved that it can be and then extended to the Teichmüller space. Okay, so then after you perform a modular transformation, you have to prove that after the modular transformation, this function can still have Q expansion in terms of the interturning operator. So this is the step where we need to construct some interturning operator from some symmetrical linear function. So that's the last step I just mentioned that recently I think I worked out. So I do not know whether this answers your question, but
yeah, I was trying to understand at what level when you do this thing, you got some other function in Q. It's interesting to see where the modules for the VOA come in your proof, but I haven't read your proof, so maybe I should look at the proof.
Yeah. So the nice thing is this: after you do a modular transformation, originally you start with the interturning operator and a given modules, right? So these are given. After you perform module transformation, it just becomes some function. Okay, there's no modules and interturning operator. So you will have to actually prove there exists submodules and interturning operator, such that this function is coming from the Q trace. So that is exactly the last step.
Okay, that's interesting.
Yeah,
That's
so that's
intuitively
the
backward. Okay, thank you.
Yeah.
So the rational theory, of course, has all these deep applications that started a long time ago
Right.
to link invariance and three manifold invariance and so on.
Mm-hmm.
And lots of other things outside of what you even mentioned.
Right.
So what do you imagine as, well, analogous, but different applications to things other than what you mentioned? For the logarithmic theory, I meant to say.
Yeah, for the logarithm theory, I think that one of the in mathematics, okay, in mathematics there are a lot of applications because the say for example, representation theory of affine algebra. We are actually interested in some of these labels which are not the labels studied by Kasia-Lustig or by us, the positive integral label. So these other labels, they are also have interesting structure, like have braided tensor category structure and so on. So our theory can be applied. Okay, so this is in mathematics,
Right,
and also
and
like
course,
in the for Virasora.
Right, so of course I'm aware of that program, and it's generalizing and extending and deepening the Kajan-Lustig quantum group representation correspondence. Yes, so that's a huge direction.
Yeah.
And beyond that, also, what else?
Beyond that, the one of the interesting development in recent years is this four-dimensional supersymmetry Yang-Mills. So physicists, they find that these all these chiral algebras inside the four-dimensional supersymmetry Yang-Mills, and many of these vertex algebra are not all these things are not rational. So these are in general that they might not even be unitary. See, if a theory is unitary, then there's no logarithm. But if they are not unitary, there will be logarithm. So the main thing that the chiral algebra, I think that people discovered in these supersymmetry Yang-Mills, they might not, these L0 might not be like the energy of the supersymmetry Yang-Mills, and therefore there's no reason that these operators must be unitary or something. In string theory, conformal field theory corresponds to the perturbative string theory. So L0 is the energy operator. So energy operator must be unitary operator. Therefore, you do not see the logarithm. In the final theory, you're putting everything together. But in supersymmetry Yang-Mills, these operators are not the energy operators. So there's no reason for them to be unitary. Yeah, so this is one of the interesting developments in physics, I think. Certainly, I do not know about. I see in mathematics there's one conjecture which is still not proved. That is for C2 cofiniteness. For C2 cofinite vertex algebra. Using our theory, we already have a braided tensor category. I conjecture that this tensor category is rigid. Okay, this is still a conjecture. Okay, even after the modular invariance, after I finish the modular invariance, I still do not see how immediately I can prove the rigidity. Okay, so there is still something that we need to understand, and also another thing that even if we have rigid braided tensor category, we still want to figure out what is the correct so-called modular tensor category structure. There are different proposals, but I think that for the C2 cofinite case should be a test case that this C2 cofinite tensor category satisfy what type of a modular inverse property should be give us the correct modular tensor category for this logarithmic theory. So this is another things that I myself still do not understand well yet, because I even do not understand the rigidity yet.
Are there more comments or questions? Well, so this was a really fabulous survey. So thank you very much again.
Thank you.
Yeah, that's wonderful. So can I just ask a general question? So when you have this this inversion element, okay, so does it take modules to modules or just combinations of modules?
What do you mean by inversion element?
Well, this transformation 0, 1, -1. I mean, tau goes to -1 over tau.
Oh, okay. This is modular transformation.
Yeah, this sort of
so the main thing
parabolic generator of SL2.
Yeah, the transformation is that in the beginning, so you just transform to a function.
Yeah.
So we do not really so that we do not really know what it is. Okay, after if you have some if the vertex operator satisfies some condition, we can prove that it is again a Q trace. But so the main thing is this: if you choose a basis of this intertwining operator, okay, you for example in the rational case, you choose certainly the irreducible modules, and then the after modular transformation, you want to in the beginning you only know that it must be a Q trace, but it's given by some module, but because it's reproducible, you can write this as a direct sum of irreducibles, and therefore there will be some coefficients. So these coefficients are the modular transformation coefficients. Mm-hmm. That's the number.
But these coefficients, are they positive? Are they just integral, or what's the story with that?
Okay, so I think that you see I myself do not really think that they have such nice property, but you see for affine Lie algebra they have been calculated, right? So these transformation coefficients. The main thing is that because I think that there are some nice property you can derive from the fact that they are transformations of the graded dimension of these integral highest weight irreducible modules. So they certainly have some very nice properties, but I myself do not know explicitly what these properties are. But see the main thing that after Verlinde gave his conjecture, people just use these character formula. They actually Verlinde himself, he used this formula to actually calculate these character for higher genus ones, and they are certainly supposed to be integer. So that's an amazing thing, because I think that so for I think even for SL2, the modular transformation actually involves something like a sign or something. And so in the beginning, you do not really see that this is an integer, but see it turned out after you apply the Verlinde formula, the fusion rule must be integer. So he indeed showed that these are integers. So I think for modular transformation, these do not have a lot of nice property, but see, it's amazingly that the Verlinde formula combination indeed give you an integer. So that's the original amazing thing when Verlinde actually derived his formula.
I wanted to ask about the associative algebras you mentioned in your recent work. Could you describe them in any way? Are they conformal associative algebras or?
Yeah, they are associative algebras.
Conformal algebras?
Not conformal, just associative algebras. So so the reason why we actually in vertex operator algebra at this stage we want to use associative algebra is mainly because associative algebra is a well-developed subject. There are a lot of theorems. So basically, we actually try to use, we want to prove something, but we find that in vertex operator algebras, we do not have such a theorem. So we reduce to associative algebra. So you need to find some associative algebra, reduce to associative algebra. Using associative algebra, you solved problem and then go back to vertex operator algebra. What I believe is that in the future, we probably just use this associative algebra, prove some basic theorem about vertex operator algebra. In the future, people do not need to use associative algebra. They only need to refer to this vertex operator algebra theorem. For example, one of the theorem I have to use, that's the reason why I developed the theory of associative algebra, is that I need to see in the classical associative algebra, there is this theorem which says that if you have a semi-simple associative algebra, and if you have a symmetrical linear functional on the semi-simple associative algebra, then this symmetrical linear function must be a trace of the algebra over some module. Okay, so this is a very sort of simple results because semi-simple algebra can be reduced to simple algebra. Simple algebra is just a matrix, and then you just a matrix, we all know such a result. So this is exactly how you actually prove, like after you do modular transformation, you get some function of Q. And how do you show that this function of Q is a Q trace? You have to just prove that there exists a symmetrical linear functional, and then it must be a trace of some associative module. And then from associative module, you can construct a module for vertex operator algebra, and then construct the intertwining operators, and then you come back to some Q trace. So that's the reason why I need these associative algebra. So here it's only associative algebra.
But what kind of associative algebra is there?
It's okay. So it depends on what kind of a condition on the vertex operator algebra. If the vertex operator algebra is C2 cofinite, then I prove that these associative algebras are finite dimensional. So it's not the same simple in general. If the vertex operator algebra, all modules are completely reducible, then the algebra is semi-simple. But we are interested in non-semi-simple one. So the condition C2 cofinite guarantees that these are finite dimensional algebras.
Interesting. Yeah. Also, you said that you describe vector operator algebras as an operand over Riemann surfaces.
Yeah.
Could you describe this a little bit more, I was interested about that.
Yeah, so this is actually, I have a book, see, they are published as an extension of my thesis. So roughly speaking, it's just this. The best way to describe this is to use the sphere with punctures and the local coordinates.
Right.
Okay, so essentially this is equivalent to sphere with some holes, but see the sphere with punctures and local coordinates is better. So the description is this: these sphere with punctures and local coordinates, they actually has a sewing operation. You just cut a disk around these punctures using the local coordinates, and then identify boundary, you get another such. Okay, so we have a sewing operation, and then the given a vertex operator algebra, we have a vertex operator. Okay, vertex operator, we have a variable, we call this z. Okay, so such a vertex operator corresponds to the sphere. Sphere is given by like the complex plane plus infinity. So the complex of plus infinity together with 0, z, and infinity as 3 punctures. And then the local coordinates are just the trivial one, which is vanishing at 3 punctures. Okay.
So this is the classical Riemann sphere apparat here.
Yeah, this is this is basically roughly speaking, it's an operator, but see, you have to be careful because I consider arbitrary local coordinates, because the arbitrary local coordinates. So you cannot solve arbitrary 2 of them. So that's why it's a partial operator. But I need this partial operator. I need all the local coordinates. Why? Because vertex algebra is meromorphic algebra. The meromorphicity need all the local coordinates. If you use only some local coordinates such that all these 2 can be solved, you will not be able to formulate the meromorphicity. So that's the reason.
So it's an infinite dimensional analytic type of operator.
Right.
It's based on the kind of familiar finite dimensional operator, but the deep part is
it's basically the same as what people call the little disk operator.
Yeah,
it's more complicated.
And the deep
main thing is that the little disk operator is a sub operator inside of this. That's
right.
And the deep part is the exponentiation of the Virasoro algebra.
Yeah, it's
and the determinate line bundle.
Right. And
those are much deeper than the finite dimensional sewing of Riemann spheres.
Right. It's mainly that I here for simplicity I do not discuss the determinate line bundle, but see, because the vertex algebra we have central charge, so you will have to consider determinate line bundle over this. So that's a complication.
Thank you.
What's the status of classification of rational conformal field theories at genus 1? There was this old conjecture by Moore and Seiberg. Could you comment on the status of that?
I myself do not really know any mathematical results about these kind of a classification, but there is a classification of so-called the holomorphic vertex algebra at central charge 24. But so this is actually originally given by Shelikin, right? But see, the Shelikin is only a conjecture. Right now, it's not the classification is not finished. Mainly, it's just because the Moonshine module uniqueness haven't been proved. Okay, so for other classification, I do not really know. Mathematically, it's too difficult. So central charge 24, if we consider only holomorphic conformal field theory, means that only the vertex algebra, all the irreducible module are vertex algebra itself. Okay, that type of conformal field theory in central charge 24, modular the uniqueness of vertex algebra, Moonshine module vertex algebra. This is sort of already finished, but still we have the most difficult uniqueness of Moonshine module, which basically not much progress.
But I mean, in physics, for example, we use the bootstrap to classify conformal field theories, and we have partial results. Is there an analogous program that at least tries to figure out how many CFTs there could be at every central charge?
Yeah. So you see the main thing. Let me say the difficulty about the classification problem in conformal field theory in mathematically. I mean, okay. So why it's difficult? Because any kind of a classification, you must work with general theory. So the main thing that for vertex algebra, the general theory is still under development. Okay, so it's in physics, the main thing that people can assume whatever the axiom you want. Okay, so therefore you can just do something. Okay, but see, mathematically, you cannot assume, like one good example is actually the work by Moy-Seiberg. Moy-Seiberg, they can assume all the axioms they want, including like a modular invariance of intertwining operator, operator expansion, and so on. So then you see, if you want to classify something, you further assume these properties. And then basically, so I can say that in physics, basically people classify is that under these conditions, you classify these. And then there is another conjecture is that the conformal field theory satisfy these conditions are exactly the class of conformal field you want to classify. So there are these conjectures, but mathematically we cannot we have to prove all these conjectures. We cannot just so like for example, if you assume all these strong properties, certainly you can classify. Okay, you can use the same method as physicists, but there's a conjecture that with all these strong assumptions, these conformal field theories are exactly the class conformal field originally you want to classify. That is the difficult part that mathematicians still do not know how to do these in many cases. I think that's the main thing.
Thank you.
Mm-hmm.